All right, folks, this is the second part of class this week, Soil Classification and Taxonomy Part 2. In the last lecture, we left off talking about spodosols, and so now we will talk about oxasols. Oxasols are represented by ox in the soil taxonomic name. Ox comes from French oxide. These are very highly weathered soils. They're tropical in nature. They are ochric in their epipedon, meaning they usually have a light, not very fertile surface horizon, but they can also have an umbric epipedon at the surface as well. The oxic subsurface horizon, meaning the subsurface soil layers, are going to have very low activity clays with a lot of iron and aluminum oxides, and they're going to have a lot of boron, which is toxic to plants. So it's difficult to grow things in these soils. They have very, very, very low base saturation, and that makes it very difficult for them to be utilized for fertility purposes. And so these tropical soils have to have a lot of amendments made to make them fertile. Histosols, ist comes from Greek histos for tissue. These are our organic soils. They are derived from plants that have only partially broken down and are growing at a faster rate than can be completely broken down in organic matter. And so you end up with this entire collection, essentially like 6 feet in some cases or deeper, of organic matter. And this is what comprises what's called a histic epipedon. We can have 12 to 18% organic matter. We can also have mineral particles in these soils. So it's not just organic matter, but it just is mostly organic matter, okay? They're usually saturated part of the year. They're definitely found usually in wetland environments. They're very high water and nutrient holding soils. They have a very low bulk density. They're often mined to be used for the kind of soil that you can buy for house plants or to amend soils in the garden with. So we do have an issue with them being mined and utilized elsewhere. They're wonderful for carbon storage. They can sequester a lot of carbon, and one of the problems with them being mined and exposed to more air is the oxidation of carbon that causes excess release of CO2. And what you may have learned in your environmental science classes in college is that too much CO2 makes for an unhappy Earth. So another thing about histosols that's very interesting is their water holding capacity. When they're dry, compared to when they're wet, there's an 85% change in volume. And because of this, there's a huge issue with subsidence with histosols. So here's some cool maps kind of showing where most of the soil orders are found, where the mollisols are found, where alphasols are found, where ultisols are found, where iridosols are found, inceptisols, gellisols, spodosols, oxasols. Just kind of cool to kind of see where they're at within the context of the United States of America. And if you have the book, you can also see this on the inside and backside covers. Here's the entisols, the andisols, the histosols, and the vertisols, where they're found. And this, my friends, I'm going to link in another area on here for you to watch. I'm going to embed this in the pages, so make sure you watch this video. It's the greatest thing of all time. And as you watch it, I want you to imagine me singing along with you because it's karaoke time, people. It is time to shine. So there's some tools for taxonomy that we need, some things that we need to understand for full comprehension of the things that we've talked about today. The first is base saturation. Now, I'm not going to expect you to calculate base saturation in this class, but I do expect you to understand what it is. It's essentially the base of 4 cations that we find important, calcium, magnesium, potassium, and sodium, divided by the total number of charges available. There's diagnostic epipedons that we've talked about, molic, umbric, ochric, histic, melanic. Diagnostic subsurface horizons, or endopedons. Argillic goes with the little t. When we have clay accumulation, we have an argillic endopedon. When we have weak development, or the little w, we have cambic endopedons. When we have a lowercase s, then we have a spodic endopedon. When we have a little x, we have a fragipan endopedon. We'll go over those in greater detail. There's also moisture regimes and temperature regimes that become important. Oops. In this case, soils basically have little parking spots, and we call them ion charge sites, okay? And how many of these little ion parking spots are taken up by calcium, magnesium, potassium, or sodium as compared to how many parking spots are available then becomes base saturation. We talked about some diagnostic epipennons or surface horizons, such as molic, which is a dark-colored, thick, high organic matter surface horizon with greater than or equal to 50% base saturation. All mollisols must have a molic epipennon at its surface. Umbric is the same thing as molic, but it has less than 50% base saturation, less than or equal to. Ochric are light-colored, low organic matter, or horizons that are too thin to make the molic or umbric qualifications. Histic are surface organic horizons saturated at some time in the year that have 12 to 18% organic carbon, which is exceptionally high. We usually see maybe 5% organic matter in really healthy soils. So you can kind of see that 12 to 18% organic carbon is like drastically higher. Melanic. Now, this is an interesting one, and it's not one that I usually ask you about on exams, but I still wanted to include it here. It's a surface mineral horizon that's black from high organic matter. It's generally associated with volcanic ash, which means that it's also associated with andesol soil orders. Okay, it has a lot of organic carbon from that ash, and it's more than 30 centimeters thick and very fluffy. Now, diagnostic epipennons, kind of reviewing all five together, we've got our high base saturation molic, we've got our low base saturation umbric, and our low base saturation thin and light ochric. And then we have volcanic materials being melanic, and peat bogs being histic. When we talk about diagnostic endopennons, we have many different diagnostic subsurface horizons or endopennons. Remember that we have to know T equals argillic, W equals cambic, H and S both refer to spodtic properties, and X refers to phragmic properties. So in the epipennon at the surface, we could have molic, umbric, ochric, or histic. But in the endopennons, the subsurface, we could have horizons with these subsurface diagnostic criteria, and that gives us a clue into what kind of endopennon it has. So if you have a series of BT horizons, you have an argillic endopennon. If you have a series of BW horizons, you have a cambic endopennon in your subsurface. If you have a series of BHS, BH, or BS horizons, then you have spodtic endopennon. If you have a series of BX or BTX subsurface horizons, then you have a fragipan endopennon. So, going back to these endopennons, the argillic horizons are described with a lowercase t. There's alluvial accumulation of silicate clays. There's clay films on the beds and the pores called clay skins or cutans. And we classify this as a BT horizon. Now let's talk for a minute about I versus E. What is the difference between alluvial and eluvial clay movement in soils, or movement of anything in soils? If you have an alluvial movement with an I, that means you have things coming into the horizon. If you have an eluvial movement of things throughout the soil profile, that means you have things entering the soil. Exiting the soil horizon. So an example of an alluvial with an I horizon would be an E horizon. Ugh, I lied. An example of alluvial with an I would be a horizon of things coming into it. So you would have a B horizon. And remember, B horizons are horizons of accumulation. So, for example, maybe a BT horizon or a BH or a BS horizon would all be alluvial with an I, whereas horizons with eluvial with an E are losing items. So we would have something like an E horizon because things are exiting out of it. Diagnostic endopennons are continued here. We're going to be looking at weakly developed horizons, and generally this goes with the B horizon, and describes a cambic endopennon, where we have the evidence of color and or structure development, but we don't have clay accumulation. BW, weakly developed, a little bit of color change, but no actual movement of materials into the horizon yet. weak development. Spodic horizons, characterized by H or S, BH, BS, or BHS horizons, have illuvial, things coming into them, accumulation of humus, sesquioxides, and they're typically going to be in coarse textured soils in cool climates. The X refers to endopedons that have a fragipan. These are weakly cemented dense horizons, and they're usually associated with more than 50% of upland soils in the Loess region. We designate them either a BX or a CX, and generally you find them to have a loamy texture. Endopedons with oxic horizons have very highly weathered accumulations of low activity clays, lots of iron and aluminum oxides, very low base saturation. These are going to be associated with oxisols. Other important diagnostic endopedons are the AP horizon, which is a surface horizon that has been plowed, or the BG horizon, which is a horizon where water has logged the area, or it has basically been just so saturated that the iron has turned to a gray color because it's been reduced. There's very poor drainage suggested by this. It's dominantly gray in color, and we call this a BG horizon, and this is also evidence of a cambic horizon. There's regime classes that are listed from wettest to driest, aquic being the wettest, xeric being the driest. In temperature regimes, quiet is the coldest, whereas thermic is the hottest. So let's do a quick review to catch up. Which soil orders are the youngest? Which soil orders are the oldest? Now, if you answered youngest, soil orders being entasols and inceptisols, then you are correct. And if you answered oldest being ultisols and oxisols, you are also correct. Without knowing a soil's order, how could you get a good idea of its relative age or weathering? Some clues include the type of mineralogy that's there. If it's very high in aluminum and iron oxides, it tends to be older and more highly weathered. Remember that we start from the back of the name and we identify order, suborder, great group, subgroup, family, and then series, which is at the front of the name. Let's practice on some soils. If I were to give you those long soil names and each one of them ended with these words, what soil order would you say belongs to Boralf? Alphasol, that's right. What soil order belongs to Argid? If it ends in id, that means it's Aridisol. What soil order goes with fluvent? If it ends in ent, that's right, it's an entisol. What soil order goes with hemist? If it ends in ist, it's a histisol. What soil order goes with xerult? Ult, U-L-T, ultimately weathered, ultisol. Awquartz, basically this soil name ends in ert. Remember Latin to turn is vertisol. Ocrep, meaning it ends in ept, is inceptisol. It's at its inception, it's young. Udal, ending in dol for the best soil in the world, mollisol. Turbel ends with L, which stands for gelisol. Vitrand, and, ends in and for andisol. Torox, ending in ox, stands for oxisol. Aquad, ending in odd, stands for spodiosols. Summing it all up, looking at figure 3.8 helps immensely. There's tiny terms here that kind of help bring home some of the information for you, but none of this is required. Now we're going to talk about the soil survey, and we're going to be spending quite a bit of lab time in this class looking at the soil survey. Ultimately, soil surveys are important because it's a document that allows us to understand soil management characteristics for an area so that we can make decisions for building a new airport, installing an irrigation system in the best place, placing new soccer fields, arranging a housing development, estimating crop yields, determining the animal units of a pasture, placing landscape plantings, forestry. The list goes on. Really understanding the soil beneath your feet becomes especially important. In this neighborhood, a contractor failed to consult a soil scientist prior to building, and after residents moved in, roads started moving, sidewalks started getting turned up. There was even a chimney that fell off someone's house. Now, what this indicated was that the soil was moving. And what have we learned about soils that move? Soils that invert on themselves have vertic properties. A vertisol was at the base of all of their problems. And had they consulted an actual soil scientist, they would not have been cleared to build here. They would have had to remove the soil, place pilings much deeper to withstand the movement of the soil without wrecking, cracking, etc. Don't make this mistake, folks. Make sure you consult a soil survey. It's essentially a digital map of the world. It provides spatial variability in soils both vertically and horizontally, on a small scale, a medium scale, and at large scales. We know that variation in soil properties most often has to do with local topography, the effects of organisms, and the thickness of plant material layers. Here in a field, there's an area where we cannot get plants to grow. And what we found out was that the soil surface, we have exposed carbonates from parent material at the surface here, and it has made it impossible to grow plants. And a soil survey has shown this small scale variability existed. Another example of small scale variability. We see an uneven layer of silt blankets on glacial deposits of coarse sand and gravel in this Rhode Island inceptisol. The profile water holding capacity varies with the thickness of the silt, which is causing an irregular pattern in the drought-stricken turf grass at the surface. Medium scale variability often relates to particular soil forming factors, such as topography. Topography offers differing drainage classes, from well-drained areas of the soil to moderately well-drained to somewhat poorly drained areas. Generally speaking, the lower on the landscape that you get, the more poorly drained your soil is going to be, although there may be anomalies to that. Parent material can include residual, transported, and organic parent materials. Medium scale variability also shows that a set of soils only differing in one of these varying soil forming factors can be identified as either a change in the sequence of parent materials, identified as a lithosequence, similar parent materials but of different ages, meaning a chronosequence, or different topographic locations, equaling out a toposequence. A catena is when you have the same parent material, climatic conditions, different topographic location, and drainage. Again, there's a global map of soil orders and where they occur on the front and back portions of your textbook. Here it is, provided for your convenience. Large-scale variability can be shown across the United States, where we find a majority of ultisols, for example, occurring across the southeast, where heavier rainfalls and hotter climates lead to greater weathering, physical as well as chemical weathering, leading to more soil profile development and ultimately more weathered soils. We can see albasols occurring across the Appalachian Mountains. We can see mollisols occurring across the Great Plains. And surprise, surprise, iridosols occurring in the deserts of the United States of America. How do we get these maps? These are the tasks of a soil surveyor. These people are tasked to map the soils for spatial variability, characterization of the mapping units and field profile descriptions, classification of the mapping units for taxonomy, and correlation with other soil surveys, where we compare it to adjacent maps. All of this is created to create an interpretation of soil suitability for various land uses. There's two approaches to sampling soils to create a soil survey. Both start with aerial photos to get a general idea of topography and likely soil boundaries. Soil augering is traditional and it is not guesswork. This is traditionally how things are done. But a non-intrusive method, if you are unable to go out on site, is to use a global positioning system to ID sampling locations without ambiguity, or ground penetrating radar, which can help identify a BT horizon but not necessarily the depths. Electromagnetic induction can also help you identify features such as clay pans. In order to choose points to sample, you can either use the grid sampling method, shown on the top right, which is much more labor intensive and includes a lot more sampling of actual individuals' units in a grid pattern, or you can use transect sampling, which is less labor intrusive and the most popular design. It's where you take transects perpendicular to major soil landscape relationships. The result of all of this is a soil description down to 150 centimeters, or essentially 6 feet deep. The County Soil Surveyor Report is created from this information because it's needed to have this to serve as a reference for land use planners, farmers, landscape contractors, and developers. It contains the following components: a general soil map that showcases the entire color for soil associations, as well as an overview of the roads and buildings for locating a specific map sheet. It is not useful in planning for specific site use. It also includes detailed map sheets where we can see houses and individual trees, which allows for specific site planning. And then there's interpretive information, which is not only for agricultural but also for many other uses.